Evening. I'm Spot On Weather meteorologist Matthew Euler. Welcome to my next training video. And today we're going to take a look at phase changes of water. Now, this may not seem very important overall to the weather, but it does play a significant role in energy transfer as these phase changes occur. So energy transfer within the atmosphere. Just by looking at this graphic here on the title slide of the presentation, we have three various forms of water. We have a solid form of water, of course, known as ice. We have a liquid form of water, and you typically see this on a rainy day with the raindrops. We have water vapor, which is invisible molecules of water vapor gases. So there's many different types of states of water, and there's many different positions. If we look below the ice here, for example, let me go ahead and get this for you. We look here below this ice. You notice how these molecules are more rigid and locked into a place. We look at a liquid. You still have some molecules locked in together, but they're not as rigid as with a solid or ice. And then with a water vapor, you see these water molecules. They're more free to move about, and it's more random as far as the organization and structure, and not really a rigid structure when you have water vapor as a gas. So let's get right into the training. We'll start now with the overview. Big things here with the phase changes of water, that water is continuously changing phases. With water, we have tremendous amounts of latent heat, or what's known as hidden heat. When I say latent heat, just think of it as a hidden heat. This is a type of heat you really can't sense with a thermometer. But latent heat, this hidden heat, is very important in atmospheric processes as far as causing these water phases to change. So again, tremendous amounts of latent heat or hidden heat exchange with the environment. And then this latent heat is energy stored within water molecules overall, and it is the required energy to change a substance from one state to another. And then finally, these phase changes are important in the transfer of atmospheric energy and affect the development of pressure systems, which we just talked about pressure systems. We just talked about high and low pressure systems in the last training video. All right, so let's break down six phase changes of water rather. And we're going to talk about melting, we're going to talk about evaporation, we'll talk about sublimation, freezing, condensation, and deposition. Let's start with melting. Now, what happens with melting? You may have observed this on a winter day where at one point in time, maybe you saw ice on the ground and the sun came out and that incoming solar radiation helped to heat that area of ice and turn it to a liquid puddle. That's an example of melting. It occurs when water molecules are going to change from a solid form to a liquid form, ice over to a water. During melting, the ice, what's going to happen is it's going to absorb the heat energy from the surrounding air, and these molecules are then going to change from a lower, more rigid, more locked in state to a medium energy state when you go from a solid to a liquid. These molecules require more energy and gain this energy from the surrounding air, and this has the effect of cooling the atmosphere. Now, 79.7 calories of latent heat or hidden heat is absorbed per gram of water when melting occurs. And an example also, besides the winter day one I gave you, watching ice change to a liquid puddle, think about melting with the ice cubes in a glass of lemonade. This melting occurs as that ice is broken down, the rigid molecules of the ice cubes is broken down into the liquid, and you can feel the cooler drink as that ice melts in it. So basically think of melting as cooling your glass of lemonade. Evaporation is the next phase change we'll talk about. This occurs when water molecules change from a liquid to a gas. So now we're going from that puddle. Let's say it rains and there's puddles left on the ground. Then the sun comes out. The incoming solar radiation will evaporate some of those puddles, and eventually they'll just completely look like they disappear, right? So this is an example of evaporation, going from that liquid, that water puddle, to nothing, going from a water to a vapor. During evaporation, again, the water is going to absorb that heat energy from the surrounding air, which then cools the atmosphere. Molecules are changing from a medium to now a higher energy state. Um, let's just put it this way for energy states. Solids are going to have the lowest energy state because the molecules are really locked into place. Cooler the temperature, the less the molecules can move around. So that's more of a low energy state, a solid, like an ice is an example. A liquid is a medium energy state, so we do have some motion of the molecules now. And then the high energy state would be a gas. And we're going from a liquid to a gas or to a water vapor, and that's going to result in a transition of energy from a medium to a high energy state. So water molecules are going to require more energy to go from that medium state to the higher energy state to the gas. The more energetic, faster moving molecules in the environment then come in contact with and speed up the slower molecules. So you got faster moving molecules zipping along in the environment. They come in contact with, speed up the slower molecules, and the overall molecular motion of the water is going to increase. The atmosphere is going to cool 597.3 calories of this latent heat per gram of water. Now, I gave an example of the puddles already that disappear on sidewalks after rainfalls. I'll give you another example of evaporation, and it's quite common in your kitchen. When you boil a pot of water, okay, you boil a pot of water to cook something. It could be something like macaroni, where you put that macaroni in the pot of water, you're boiling the water. What happens over time is that water, as it's being heated up, we're going from that medium to the higher energy state. It's transitioning as it's heated the water. You will see that cloud, that vapor cloud above that heated pan. And that's another example of evaporation right there in your kitchen. The next phase change we'll talk about is what's known as sublimation. This is a phase change that absorbs or takes in energy, and it basically occurs when we go from a solid to a vapor. So if we were to go from an ice straight to a water vapor, to the gas water vapor phase, without going through any kind of liquid stage. So you're going right from a solid to a gas, ice to water vapor. This cools the atmosphere by 677 calories of latent heat. So it's quite a bit of energy it takes. 677 calories. Molecules are going from that lower energy state, okay? So we're initially in ice, right? That's the lowest energy state possible. The molecules are locked into place. And then we go to a high energy state, going from that ice straight to the water vapor without going through a liquid, the liquid process first. So sublimation has the greatest cooling effect, and it requires the same amount of energy to sublimate that it would take ice to melt and then evaporate. So this process takes, like I said, it's a lot of energy. It required 677 calories of latent heat. It's very common over snow-covered ground in northern latitudes, where you can go directly from that snow or that ice state to a vapor. All right, so now let's switch gears and talk about the freezing phase of water. This occurs when we go from a liquid to a solid. We go from water to an ice. So we're going from a medium energy state to a low energy state. During this phase change of freezing, the molecules, again, I just said it right there, I'm already ahead of myself here, go from a medium to a low energy state. They release energy. Think about this. If you're freezing something from a liquid to an ice or a solid, energy is that latent heat energy is going to be released to the surrounding air, because the overall water itself is cooling, right? Molecules are going to release this excess energy to the surrounding environment. It's going to warm the surrounding environment a little bit. There are 79.7 calories of latent heat released per gram of water in the freezing process, the exact amount of energy that melting absorbs. So those are same numbers there. Melting and freezing, same amount of required energy, 79.7 calories of latent heat. Condensation, next phase change. This occurs when molecules transition from a gas, that water vapor, to a liquid. So going from that water vapor to a liquid or water, molecules go from a higher energy state when they're a vapor or a gas to a medium energy state as a liquid. Therefore, that releases heat energy and warms the atmosphere further. The amount of excess energy or latent heat released is 597.3 calories per gram of water. And think about it, I got a couple examples for you. We'll talk about this one first. Water on the outside of a lemonade glass. Okay, so you can relate to this on a hot summer day. All right, just grab a glass, throw ice in there, fill it up with whatever your favorite beverage is, right? After a while, you're going to see water on the outside of the glass, whatever the beverage is. It could be lemonade, it could be soda, it could be tea. You have overall condensation occurring on the outside of the glass. It gets really wet on a hot summer day. Another example I want to give for condensation, and it's very important in the atmosphere, is in a tropical system. As the air rises, it cools, it condenses, and when it goes from that condensation process from the vapor to a liquid within a developing tropical cyclone, it releases tremendous amounts of heat energy to the surrounding air, further making things more unstable and for that tropical cyclone to continue to develop. Deposition. This is another phase change. This releases heat energy. The molecules are going to change directly from a gas, a vapor, to a solid, vapor to ice. So we're not going to go through any kind of, liquid state. We're going to go straight from a vapor or a gas to ice, a solid. This warms the atmosphere, and because you go from a high energy state, from a gas, to a low energy state, a solid, they have excess energy. The molecules have excess energy. The 677 calories of latent heat released are the same amount absorbed during sublimation. An example of deposition would be on a cold winter morning where you see frost on your car windshield. You're going from a vapor to an ice without going through any kind of liquid stage. You're going directly from vapor to ice. Here's an overall summary of all of the phase changes of water. These are very important again. So you see the condensation, the deposition, and the freezing process warms the atmosphere, okay? And you can kind of see the arrows here. So condensation is going from these water molecules on the left to the liquid. If we go to freezing, we're going from a liquid over to a solid, okay? When we freeze, we go from a liquid to a solid. And when we go through deposition, we go from a water vapor, the water vapor molecules over here, we go from a vapor state directly over to a solid state. We bypass this liquid state in deposition. And all three of these are going to warm the surrounding air. Okay, they're going to release heat energy to the surrounding air. If we look down here on the bottom, evaporation, going from a water vapor to a liquid. We've got melting, which goes from a liquid to a solid. Solid to a liquid rather. So we're going the opposite way here, right? From solid to a liquid is melting. And then we have sublimation, which basically goes from a solid directly to a gas or a vapor without going through a liquid state or a liquid portion of the phase change. And when you talk about evaporation, you talk about sublimation and melting, they all result in cooling of the atmosphere. And think about on a hot summer day when let's say you're outside in the sun and the humidity is really high, you have a lot of moisture in the lower atmosphere, you start sweating a lot, right? Evaporation is actually a cooling process at which you have basically, let's say the wind is blowing, it blows over your sweaty arms, that evaporation is going to occur on your skin surface and it's going to result in a cooling effect for you. So just kind of think about that in the same state. Now these water vapor molecules again are gas. This is a gas. When we talk about water vapor, has a high energy state. A lot of these molecules are farther spaced apart, and they move a lot quicker in this water vapor stage. The liquid stage is the intermediate energy state, and then over here on the right, that solid state is a low energy state. So low, medium, and high. For atmospheric applications now, why does this matter, these phase changes of water? Water molecules do not change temperature. So the temperature of the water molecules is not going to change. When we're talking about latent heat, we're talking about during these phase changes of water, the heat is solely used to change the phase of the water, whether we're talking from ice to a liquid, liquid to an ice, or whatever the process, a vapor to a liquid in condensation. Water molecules are not going to change in temperature when changing phases. All the latent energy is used to make these phase changes happen. There'll be no sensible temperature, like you won't sense any kind of heat during these phase changes until after the phase changes are complete. All energy or latent heat released or absorbed goes into changing the phase of these water molecules, which has a direct effect on the surrounding atmosphere. All right, so let's take a look at an atmospheric application. Let's say you're a forecaster, all right? Let's say the temperature is 5 degrees Celsius, so that's about 41 degrees Fahrenheit, when it begins to rain. Let's say it's the winter season, okay? So it begins to rain at your location. The temperature is 5 degrees Celsius or 41 degrees Fahrenheit. There's many liquid rain droplets, however, that are evaporating on their way to the ground. So sometimes there's a case in which we have a pretty significant dry layer of air beneath the cloud base. So between the cloud and the ground, there's a lot of dry air. So initially what happens is, as these liquid rain droplets fall through the atmosphere, come out of the cloud and go towards the ground, they are going to evaporate because of all the dry air. And when that happens, evaporation, that's a cooling process. So on their way to the ground, these liquid rain droplets and the energy absorbed by the evaporation cools the atmosphere. Evaporation is going to cool the surrounding atmosphere. And what's going to happen is the temperature, perhaps in this case, it drops down to 0 degrees Celsius, which is 32 Fahrenheit. So a good 5 degrees Celsius drop, or about a 9 degree Fahrenheit drop in temperature. That rain then changes to snow because of this evaporative cooling effect from the cloud base where the liquid rain droplets come out to the ground because of that initial dry layer of air close to the ground. So your temperature falls to freezing point, the rain changes over to snow, and you're completely surprised because you didn't account for the evaporational cooling. You just saw 5 degrees Celsius, you're like, oh, that's warm enough for rain, but you didn't take into account the evaporational cooling aspect as that rain fell from the cloud to the ground. And this is just one example of how the phase changes of water can either add or subtract heat of the surrounding air. I gave the example earlier about tropical cyclone development. Condensation is a big energy producer for growing hurricanes. As the air rises very sharply within what is known as these hot towers outside of, let's say, the center of circulation of a tropical cyclone, you get really strongly rising air motion, you get cooling and condensing, and as the air cools and condenses through the process of condensation, again, it's going to release a lot of heat energy to the surrounding air, and that's going to add increased instability, unstable conditions, and those clouds will continue to grow taller and taller. Not to mention adding a lot of energy for that hurricane to kind of tap into and get stronger. So just some great atmospheric applications. I hope you enjoyed this training this evening. Here's some upcoming training, by the way, that I plan to cover. The next training will be on cloud formation. So we'll examine the different processes of how clouds form, what atmospheric processes causes the air to rise to get these clouds to form. We'll talk about fog, how fog forms and the various types of fog that exist and what causes and produces those various types of fog. We'll also examine air masses in a future training video. This is very important, specifically in the wintertime when we have stronger storm systems kind of tapping into these various air masses. And then we'll talk about fronts as well. And then beyond that, we have many more topics that I'm working on that are ahead, from convective type severe weather. We'll look at many, many more to follow. I can't wait to share these all with you. Hopefully you're learning something here during the summer season with just basic meteorology concepts. So that's all I got for now, everybody. Until next time, take care and God bless everyone.